Okay, great. So we're here to discuss the problems of AtCoder Beginner Contest 305. So I solved the first 6 problems. So these are the 6 problems that we'll be discussing today. Let's start with problem A. So in this problem, we're said that there are water stations in every 5 kilometers starting from 0 up to 100. So we have a water station at 0 kilometers, at 5, at 10, and all the way up to 100. And we're given a point, let's say N, and we need to find the closest water station to it. Yeah. So if the points are like this, not 16 like that. So any point that we get might be exactly on top of a water station, or it will be in between 2 water stations. So what we're going to do is we're going to find the water station that is previous to the given point and the water station which is the next to the given point. And the closest of the 2 of them will be our answer. So let's say we get the value 17. So as we know that the water stations are 5 kilometers apart and they're starting from 0. So how can we find the water station which is right before it? We can take the value 17 by 5 and round it down. So this will give us 3. And if we multiply this by 5, this is going to give us 15, which is the closest water station to the left of 17. And if we just add 5 to it, we get the closest water station, which is in front of 17. So among these 2 stations, we're going to check the station which is the closest. So let's look at the code. Yeah. So here at first, I'm calculating the water station, which is in front of the current water station. So we need to get the value n by 5 rounded up. So n by 5 rounded up. We need to get this value. This can be done using this formula n plus 4 by 5. So we don't need to include floating points here. We can find the ceiling value like this, and if we multiply it by 5, then we'll get the next water station. And to get the previous water station, we just subtract 5 from it. So now, whichever one is the closest, we'll store it at the val variable, and then we print it. So did you guys have any other alternate approach to this problem?
I did. What I did was I moduloed it with 5 and also took another variable, basically n modulo 5.
Yeah.
Sorry, 5 minus n modulo 5. So then I will check which is minimum, like n modulo 5 or n minus n modulo 5. So
I understand.
If the n modulo 5 is minimum, I will just subtract it from the number. Otherwise, if the later is minimum, I will just add the number.
Yeah, I understand. So you figured out these 2 values and then picked whichever one is the smallest, right?
Yes.
Yeah, okay, yeah. Interesting. Okay, so any confusions in this problem yet? I guess not. So let's move to the next problem. So in this problem, we're given 7 points named A through G, and we're given the distances between all of these adjacent points. So the distance between A and B is 3, distance between B and C is 1, and so on. So these are if you notice that these are the first 6 digits of pi. So this seemed really interesting to me, 3.14159. I did notice it during the contest, so it's a little bit of trivia. Okay, so we're given these distances, and in the problem input, we'll be given 2 of these points. So we can be given B and F or T and C, and we need to find out the distance between these 2 points. So this can be done using a prefix sum array, because if you need to find the distance between, let's say, C and E, so we have the points A, B, C, D, E, F, and G, and the values are like this. I bet this is 9. Yeah. So if we want to find out the distance between C and E, what we can do is we can find out the distance from A to E and subtract the distance from A to C. So this is what we do to get the distance from C to E. So we can just create a prefix sum array and then do this. We can subtract the distance up to C from E to get the distance between C and E. So this is what we'll do. Let's take a look at the code. Here I took the values. So I just calculated prefix sum in my mind. So I didn't bother running another loop. So then finally, we're taking the characters and input. And for these 2 characters, we're just taking the difference of the prefix sum. And we have to take the absolute value because it is not guaranteed that the first point will be before the second point. So the points can be like this, points can be E and C. So then the distance that we'll get will be negative, and we just need to print the absolute value. Yeah. So this was problem B. Any other interesting alternate approaches to this? I guess this is a pretty standard approach. So yeah. And if you guys have any confusions, you can feel free to ask. Yeah, okay, great. So let's move on to the next problem, problem C. So in this problem, we have a grid, we have a n by m grid, and in this grid, initially we had a block of hashes. So initially, let's say this was the grid. And there was a block of hashes somewhere in this grid. So all of these values were hashes. And the character from the statement took out exactly one of these hashes. So if we had this block, he could have taken out any one of these 9 hashes. Let's say he took out this hash. So we're left with this grid. So we have to figure out the position of this cell, the position of the hash that was taken out. So yeah, so I want to know your guys's approaches first. Then I'll talk about mine. So I used an approach similar to a direction vector. So I checked all the, okay, wait, let me just give an example. So there are some possible cases. So let's say the block was like this, the block of a hash. He could have taken out hash from any one of these 4 corners. This is case 1. Case 1 is corner cell. Or he could have taken out hashes from any one of these edge cells. So this is case 2, edge cell, or he could have taken out the hash from any one of these middle cells. So case 3 is middle. So what I did was I checked for all these possibilities. If he did take out, let's erase these values. If he did take out the cell from the corner, then this cell would contain a dot, and these two cells adjacent to this cell will contain hashes. So if he took out from here, then these two will contain hashes. So for any corner cell that he took out, there will be two adjacent cells which will contain hashes. And this is case 1. So for case 1, we need to check if there is a cell which contains a dot and there are two adjacent cells like this that contains hashes. So it can be these two cells or these two cells or these two cells or these two cells. So for a corner cell, these 4 possibilities can be. And if it was a middle cell, let's erase this. So if this was a cell in the middle, then these two cells would contain hash and this cell would contain a dot. And similarly for here, here, or here. So for a cell, if it is an edge cell, we need to check the two adjacent cells horizontally or vertically if they contain hashes or not. So this is case 2. And if it is in the middle, all 4 adjacent cells need to contain hashes. But this case is covered by this case as well as the case of the corner. So because we check these 2 cells for hashes in the corner case, so we'll already get this cell if we check for corners. Okay, so this was my approach. For each cell that contains a dot, I checked all these cases for hashes, and whichever one satisfied, I printed that cell. So I'll quickly share my code with you guys, and then I'll learn about your approaches. I think there are some interesting approaches out there. So problem C. Yeah, what I did was at first I took 2 direction vectors, dx and dy, similarly to what we do when we run a DFS or BFS on a grid. But here, the direction vectors contain pairs for the 2 cells that can be adjacent to a cell. So if it is a corner cell, then we need to check these 2 cells. So a pair will contain the difference to these 2 cells from a cell. So that is what I'm doing using these direction vectors. And then at first we take input, then this is a pair for storing the answer cell. And when we go to each cell, there are 6 possibilities. As you can see, the direction vectors contains 6 pairs. So there are 6 pairs here in the direction vector. So for all these 6 pairs, there are 2 adjacent cells. So nx1 and ny1 is one cell, and nx2 and ny2 is another cell. So we're going to check if these 2 cells are valid or not at first. If they are valid, that means these 2 cells lie inside the given n by m constraints. Then we're going to check if s of ij is a dot or not, and if these two cells are hashes or not. If they are, then we update answer, and then we can break out from this loop. And then afterwards, we just print the answer cell. Okay. So yeah, someone said we'll check 4 sides, and if any 2 sides are hash, and if present index is dot, return IJ. Yeah. That is also correct. So any other approaches? There might be an easier approach than mine. As someone said, you just need to check all the 4 adjacent cells of a cell, and if any 2 of them are hashes, then it is valid. Yeah, that sounds like a more simpler solution. Yeah, so let's move on. Is there any doubts in this problem? Otherwise, we're going to move to the problem D. Okay, let's move to problem D. So in this problem, the statement seemed really funny to me. So we're given the sleep schedule of some guy. So in the index, so in the time given in the first index, the person wakes up, and in the time of the second index, the person goes to sleep, then he wakes up again at the third index, then he goes to sleep at the fourth index, the time of the fourth index, and so on. So we're given some values. Let's say here 1, 2, and 3. So if the index is odd, if index is odd, then at that time he wakes up. And if index is even, then he goes to sleep. So this is what we're given, and we're given Q queries. In this Q queries, we're given a time range L to R, and we have to print the number of minutes that the guy spends sleeping in this range. So here we're given 480 to 1920, and we need to find out in this range how many minutes he spends sleeping. So let me take this example: 0, 40, 720. Yeah, so he wakes up here, wakes up, and he goes to sleep here, and here. So the difference between these two times is the amount that he sleeps. Same for this and same for this. So when we're given the window 480 to 1920, 480 to 1920, let's see how many minutes he spends sleeping. So in this given window, he sleeps the whole time. The given query time is starting from 480. So he will sleep from 480 to 720. So 720 minus 480. What is this equal to? I think this is 240. Yeah. Then he sleeps this entire period. So this is 120 plus he wakes up, he finishes at 1920. So from 1800 to 1920, he will sleep. This is also 120. So this is a total of 480 minutes. And if we check, yeah, the answer is 480. So this is what we'll have to print in the queried range, how many times he spends sleeping. Yeah, so we'll need binary search to solve this problem. So let's see why we're going to use binary search here. Yeah, so we have some time windows in which he sleeps. So let's store these windows, and obviously these windows are going to be in increasing order. So he goes to sleep in these positions. So in our time window L2R, let's figure out the complete windows in which he sleeps. So in L2R, we're going to figure out all these windows which lie completely inside L2R. And there will be some intersection with some other sleep window. We'll figure out. So there are some sleep windows here. And let's say the queried range is like this. So using binary search, we're going to figure out this range, the range that lies completely inside the queried range. And then we're going to have some extra intersection at the end and at the beginning. And then we're going to manually add these two values. But we can add this at the range of this value if we find it using binary search, and we can keep a prefix sum of the summations of these ranges. So if this is 2, 3, 7, 4. So these are the time windows. We can keep a prefix sum, and when we get the range that lies completely inside, we can get the total time in this window using just the prefix sum array. So that is what we're going to do. And anyone have any doubts up to here in my approach? No. Okay, great. So let's take a look at the code. So this is problem D. Yeah. Pardon my code. I used some of my own language words here. So yeah, so we have n, and we also have the array. So we took the array in input. Then in this array, so yeah, can anyone confirm if you can see my cursor or not? You guys should be able to see my cursor.
You can.
Okay, great. Yeah. So we have some extra vectors here. In the array2 vector, I'm going to store the differences. So the sleep schedules like these windows, we're going to store all these values in the array2 vector, and then we're going to take a prefix sum of this vector. And we're going to also store two other vectors. One vector will contain this vector, will contain the times in which he goes to sleep, and this vector will contain the times in which he wakes up. These two vectors will help us in the binary search process. So we take the prefix sum array and we calculate prefix sums, and then for the queries we take L and R. And how are we going to find the range where he completely sleeps the whole time? So we're going to use lower bound and upper bound. So if we run lower bound on the vector in which he goes to sleep, and we run lower bound of L in that, we're going to find the first index which starts after L, and using upper bound in the vector where he goes to sleep, we're going to find the first index which doesn't lie inside the queried range L2R. So the valid range will be in1 2 into -1. So this whole range is going to be added to our answer, the sum of this whole range. So that is what we're doing using the prefix sum array. prefix of into minus prefix of in1. So then we just need to add two values, the extra time in front of this window. So let me resound this. So we got this range using binary search, and we need to include this extra window and this extra window to our answer. So this is what we're going to do. At first, I'm adding the intersection or adding the extra time in front of the window. So the first index, which is index in 3, which I calculated using index 1, and that is the index in the original array of where he starts from. So in 3 is the index in the original array, but in 1 was the index in the array where he goes to sleep. So we calculated index 3 in the original array, and if the value of in3 minus 1th index is greater than L. So in this window, so this index will be in 3 where he goes to sleep, and this lies in the queried range. This index is in 3 minus 1, and this needs to be greater than L. So I'll draw it again. So there are some windows here. So this point needs to be greater than L. So if L is here, then this much will be added to our answer. But if L is here, then nothing will be added to our answer, because this time he spends waking up. So he is woken up during this whole time. So if L is less than this point, then we can add that to our answer. So then we're going to add array of in3 minus 1 and max of L and array in3 minus 2. So why are we doing that? Okay. This point is array of in3 minus 2. If L is here, then we need to add this much. But if L is here, we need to add this much. So we need to take the max of array of in3 minus 2 or L. So we're taking max of array, max of L and array in 3 minus 2, and subtracting that from array in 3 minus 1. And I just took the max of this and 0 just in case, so I don't get a negative value. But this shouldn't occur. So similarly, I'm going to take the extra values in front of the windows in a similar approach. So this is what I'm doing here. I'm adding the extra times that is spent sleeping. Then we can just output the sum. So any doubts? And let me hear about your guys' approach for this problem. I think binary search is the approach here, but there might be some more subtleties that you guys did. Anyone wants to speak about their approaches? Okay, so I guess not. So let's move to the next problem. So we have two more problems, E and F. Sir, if possible, can you share this code? Yeah, I'll share with you this. So the code for problem D, right? Okay, here we go. Okay, so now we have problem E. So one question, anyone attempted CodeChef starters? I think it was 2 or 3 days ago. Any one of you attempted that contest? So this problem E is exactly the same to one of the problems of CodeChef starters. So let me just search it up. So this problem mail deliver is exactly the same as this problem. So it was only like 2 or 3 days ago. So I was really surprised to see this. And I also just took my code from that problem and just modified like 3 or 4 lines and then submitted. So yeah, so it was a really big coincidence that 2 of these big platforms have a coincidence like this in a matter of 2 or 3 days. Okay, whatever. So yeah, so let's take a look at what the problem says. We have a graph of n nodes which has m edges, and the vertices are numbered from 1 to n and the edges are numbered from 1 to m, and we are given edges where ith edge connects vertices ai and vi. So there are k security guards which are numbered from 1 to k, and the guards will be in distinct vertices. No vertex will contain more than one guard. So there is a capacity of a guard, so which is hi. So a guard can guard a vertex which is at most hi distance away from that vertex. So let's take a graph. So let's say we have a graph like this. Yeah. So let's say on this vertex we have a guard here, and he has a strength of 3. So let's say he has a strength of 2. So he will be able to guard these 2 vertices because they are one distance away, and he will be able to guard these vertices as well because they are 2 distance away. But if there were some other vertex like this, he wouldn't be able to guard these vertices because they are more than 2 distance away. Okay, and he can also guard this vertex. Okay, so there are k security guards like this, and we have to find out the vertices which are guarded by at least one guard, and we need to print them in ascending order. So there are more than one guard, so there can be one guard here. So there can be one guard here, one guard here, one guard here, and they can have different strengths. So this can have 1, this can have 3, like that. And we need to find out all the vertices which are guarded, and there can be some vertex which isn't guarded by any one of these guards. Okay. So let's see how we find the number of vertices which are guarded if there is only one guard. So let's say there is a guard here, and he has a strength of 2, similar to the previous example. So can anyone tell me how can we find out the vertices which are guarded by this guard? Anyone? You can write it in the chat too if you feel uncomfortable speaking. DFS till depth 2, yeah, correct. So we can run a DFS till depth 2, but there is a problem with the DFS. DFS might not always choose the shortest path. So we need to choose the shortest path while deciding if this vertex is guarded or not. So what can we do? Which algorithm can we use to find the shortest path? So yeah, we can use BFS to find the shortest path from some node. So we're going to run BFS from this node and go up to the vertices which have a distance of at most 2. So this vertices has distance 1 and this 2. So when we find the distance up to 2, then we stop. So all these vertices are guarded using this guard. Okay, so this is how it works for one guard. But what if there are what if there are 2 guards? So let's say there is another guard here. It has a strength of 2 as well. So what do? We can run a DFS from here, a BFS from here to find out all the vertices. And we can also run a BFS from here to find the vertices which are covered by these. But K can be really large. K can be up to, what is it, 20 to another 5, I think. Yeah. So K can be up to 20 to another 5. So we cannot run separate BFSs for all these guards. What can we do is we can run a multi-source BFS. So it is called a multi-source BFS. And in a multi-source BFS, there are just it is exactly the same as a BFS, but there are more than one source vertex. So in a BFS, we start the BFS by pushing the source into the priority queue. So we do PQ dot push the source vertex. So let's say 1 or something. But in a multi-source BFS, we at first push all the vertices and then we start the BFS algorithm. So we can do this here to find the vertices which are guarded, but BFS will not work here. What we need to do is we need to visit the cells prioritizing strengths. So if one vertex can be visited, okay, so at first for this guard, if we visit these vertices here, then from these vertices we can visit the vertices which are 1 distance away. From this vertex we could have done 2, but from this vertex we can visit the vertices which are 1 distance away, because we already exhausted 1 distance here. So if this was P here, we could have gotten P minus 1 vertices distances from this vertex. So if we can reach some vertex using A strength from one guard and using B strength from another guard, it is beneficial if A is greater than B. It is beneficial to visit its adjacent vertices using the strength A, because A is greater and we can visit more vertices using this strength. So we need to prioritize visiting cells by the strength, and whichever vertex has the bigger strength, we need to visit that vertex first. So this is similar to a Dijkstra approach, and we just need this will be just multi-source Dijkstra instead of multi-source BFS. So this is what we're going to do. We're going to push all the cells which have guards on them, and we're going to push them in a priority queue. So in that priority queue, the strings will be ordered from highest to lowest. And when we do this, the priority queue will give us the top element, which contains the cell which has the highest strength. So then from there, we do that. We run Dijkstra from that. So let's take a look at the code. Yeah. So here we take n, m, and k in input, and we also take the graph in input, and this is the strength of the guards. This is the guard at the x-axis vertex, and the strength of the guard is di. So we have another array which will store the strength of the riders. So this is the riders array. It will contain di for each rider. So we have a priority queue, and in it, the priority queue is defined in a way that the smallest value will be kept on the top. So that is why when in the riders array, when an index contains non-zero value, that is when a guard is on that index. So we're going to push that guard into the priority queue using the distance, and the distance is, I'm using negative value here. So if the strength of some rider or guard is -5 and another one is -2, -5 is smaller, so that will be kept on the top. That is why I'm using a negative symbol here. So I'm using distance of y equals to minus rider's I. Then we're going to run normal Dijkstra algorithm here. While the queue is not empty, we're going to take the top element, and if the distance is not equal to the minimum distance, we continue. Also, if the distance is equal to 0, so that means the guard has 0 strength now, so we cannot do anything, we just continue. Otherwise, just the guard has still some strength left. So we visit the adjacent vertices of this vertex, and if we can relax that vertex, we relax it and push it in a queue. So afterwards, all the vertices that are visited, so the distance is not equal to infinity, we push those vertices in the v vector, and then we can just print out all those elements from the vector. Yeah, so this was the approach. So any doubts? No doubt. Okay, great. So this was problem E. This is done using a multi-source Dijkstra algorithm. This is the first time that I used multi-source Dijkstra in a problem. So in the CodeChef contest, I just copy pasted it here. So that was the first time I used multi-source Dijkstra. So this problem seemed pretty interesting to me. So let's move to the next problem, problem F now. So yeah. So this problem is an interactive problem. So we have a graph which is hidden from us at first. Will only be given the number of vertices and the number of edges at first. And we're sitting at node 1 at first. So we have a graph like this. So we're sitting at node 1 at first. So we have a pointer at node 1. And at each moment, we're going to be given the adjacent nodes of the current node that we're sitting at. So at first, we're going to be given the indices of these 3 nodes. Let's say they are 2, 3, and 4. So we're going to be given the number of adjacent nodes, that is 3, and we're going to be given the 3 nodes, 2, 3, and 4. Yeah. So now we can go to any one of these 3 adjacent nodes, and we can keep repeating the process. So let's say we choose to go to the node 3, then the pointer will be moved to node 3, and we're going to be given the adjacent nodes of this node. So the adjacent nodes are 1, 2, and this node. Let's say this is 5. So there are 3 nodes, and the nodes are 1, 2, and 5. So we can also go to the adjacent nodes of this node from here on. So our task is to go to node n in at most 2n of these operations. So we can do 2n move to an adjacent node operations, and we need to reach the vertex n. Yeah. So the number of queries 2n is really special, because this tells us that for each node we can come to this node at most 2 times. So this is what we can do. So let's say we're at this node. We can go to its adjacent node, and then we can come back. We can go to this node, then we can come back. We can go to this node, and then we can come back. So for all these nodes, we're using 2 operations. Let's take a bigger tree. Let's take a bigger graph here. So we're going to run DFS on it to solve the problem. And as I said, there are 2n operations, and for each node we're going to do 2 operations for each node. So starting from this node, this is what we'll do. Like a normal DFS, we're going to go to this node, and we can go to its children. And when we come to this node, we see that there are no adjacent nodes. So we come back to its parent. So we did 2 operations for this. And we can go here and here. We can come back. We did 2 operations for this. And we can go here, can go here, can go here, can go here. We see that okay, so there are no more adjacent nodes, so we can come back. So we did 2 operations for this node. We can come back. We did 2 operations for this node. So when we run a DFS on a graph, we get a DFS tree, and in a tree, this is exactly the property that we never visit. So this is what we do. We go to some vertex and then we come back. So it will never require more than 2 operations for a vertex. So that is why the number of operations is bounded by 2n, and we can simply run this TFS algorithm on it to reach node n eventually, because we'll reach all the vertices using this algorithm. So any confusions? If there are any confusions, I'll explain it again. Otherwise, I'll explain my code. Okay, great. So let's take a look at the code. I got a runtime error once because I wasn't doing the operation of coming back from the nodes. So when we go to a node, let's say we go to this node. When we're done visiting all the children of this node, we need to come back here. So I wasn't doing an operation here. So that is why I got a runtime error. So let's take a look at the code. Okay, so at first we take n and m in input, and then we start the DFS. So in the DFS, I also got a variable which is called got, and this variable will tell me that if I got the variable n or not. So if I got the variable n, we can just return. We don't need to do anything else. So otherwise, we're going to mark this node as visited, and we're going to take a string in input. If this string contains OK, that is the interactor telling me that we reached vertex n. So we're going to mark the got variable using 1, and we're going to return. And they're going to give us -1 if we make any incorrect queries or more than 2n queries. So this shouldn't happen, but I put this case just in case. So then if it does not contain OK or -1, then it will contain the number of adjacent vertices. So using the stoi function, we can convert a string to an integer. So we convert the string s to an integer, which is the m, the number of adjacent nodes. So we run a loop for m, and for for this m values, we get an input. We're going to push them in a vector. So this vector will be the adjacency list of the current node. So now we're going to go to all the current nodes. If at any time the got variable contains 1, then we can return. Otherwise, if the adjacent node is not visited, then we're going to visit it. So we're going to output A, and we're going to visit that node. And in that node, we're going to take input for the number of adjacent nodes of the node A. And afterwards, if we reached n, then we can just return. Otherwise, we need to go back to the parent of this node. So as we're keeping track of the parent here, we have kept track of the parent here, and when we call the DFS, we pass the parent here, so we know who the parent is. So we're going to send a request to go to the parent, and we're going to take the m values in input, but we don't need these values, so we're just taking them in input, and that it will go back to the parent anyways, because we're running DFS. So this is not really necessary. So that is it. Afterwards, our code will find the node. Yeah, so this was the code. Any doubts? Okay, great. So here, yeah. So these were the 6 problems that I solved. I also took a look at problem G, but I couldn't solve it because this is a pretty hard problem, and this problem requires Ahokorasic and matrix exponentiation to solve it. So this is a pretty hard problem. These are just a few hints if any one of you want to solve it. So yeah, this was it for the post-contest discussion. Thank you guys for attending. Okay, bye.